Let's begin. Ions and isotopes notes, page 19. All right, you're responsible for the particle, symbol, relative mass, charge, and knowing the function of each of the three subatomic particles. All right.
Wait.
So what is the charge of a proton? Positive what? Positive 1. That's important that you don't just tell me positive or negative, that you tell me the value of that positive or negative. It's positive 1. All right. What's the relative mass? Well, what does relative mass mean? And not approximate. It's not the same thing as approximate. You use relative mass all the time. You'll see like comparisons, like a stegosaurus weighed the same as 34 elephants. Well, I didn't tell you an actual mass. All I told you is its mass relative to something else. So, the mass of a proton, the actual mass of an actual proton is 1.673 times 10 to the negative 24 grams.
So it's just like 0, 0, 0.
Yeah.
So 1 AU.
Okay. Hey. Now, what does that negative 24 mean?
That there's 24 zeros.
Almost. You're close. It means that decimal point is not really there. Where is it? 24 spaces that way. And so this number is actually equal to 1.673 grams.
That's heavy.
All right,
Yo, that number's really
gentlemen. So 1 gram is about the weight of a paperclip. So this is that many places off of a gram. Now, we don't want to write that number over and over and over again. So what we did was just say, look, we're going to say that this is equal to 1, a random, and make up a unit for it. 1 atomic mass unit. Done.
Good job, Carlos.
And now we just write 1 AMU to mean that mass. And it's so much easier. So that's why we make up new units for numbers that we have to use commonly. Like, for example, eggs. Nobody says, I want you to go buy 12 eggs. What do they say? Go buy a dozen. And everybody knows that instead of saying 12, you can just say a dozen and you mean 12. And so I could say 1 AMU and I mean that number. You do not need to know that number. You do need to know this. But I wanted to explain it to you. All right, and what is the function of a proton? What does it do? It tells you what element you're looking at. Tell me the definition of oxygen. Anything with 8 protons, period. Did I say anything about neutrons or electrons?
No.
No, because it doesn't matter. Anything with 8 protons is oxygen. End of story. So it identifies the element. So since a proton is positive, the symbol for proton is a positive p, or excuse me, a lowercase p with a positive superscript.
Bless you.
Hi. Sorry. There, maybe that's better. Probably not, but maybe. Okay. A neutron. What's a neutron's charge?
Zero. Negative.
0. It's neutral because it's a neutron.
Yeah.
All right. What do you think its relative mass is compared to a proton?
Same.
Yeah, it's the same. Oh my cats, this is not working. Oh my cats, hang on. Okay, sorry if I made you like motion sick.
Are you recording?
Yeah. I can't use my phone anymore. It takes like an hour and a half to upload a video.
Hello, people.
All right. Shh, I need you back.
How did they measure that?
Oh, I don't know.
With the scale.
I know they have. There was a very famous experiment called the oil drop was electron. There was something else that I haven't taught you because I don't understand it.
How did they get that exact mass?
Dude,
Well,
There
they
are some
took something that was
seriously-
one and then took it off the
Hi.
scale and just.
there's some seriously smart people out there that were building on this information for hundreds of years. So it wasn't just one.
Oh, maybe they took an element that had like one more proton than other
And relatived it out.
and did the difference.
I don't know. All right. So there's some prop. I need your attention. All right. I'm going to draw the nucleus of oxygen. How many protons does oxygen have? All right. So 1, 2, 3, 4, 5, 6, 7, 8. There's its nucleus. Great. What's the problem?
There's no neutrons.
So I said the definition of oxygen is anything with 8 protons. There they are. What's the problem? What does that even mean? What's the problem?
It's too positive. It's too happy.
Why? Why? I mean, you're wrong. You're not wrong, but hang on. I want another one first. What's going? Do opposites attract or repel? Opposites attract. Like charges repel. So what should this nucleus be doing? It should be flying apart. Back table, I need your full attention. All right, it should be flying apart because these repel each other. So that's what neutrons do. They're dispersed in between those protons, and they literally glue the protons together into the nucleus. Without the neutrons, the nucleus just flies apart. Now, there's this delicate balance. You can have too much glue, which makes the nucleus too heavy, and so it'll start to fall apart because it's too heavy. Or you can have too little glue, and it'll fall apart because there's not enough holding those positives together. And so every element has its own sweet spot where it has just enough neutrons, not too many, not too few, to hold that nucleus together. Yes?
So when we measure it, it's the most stable.
Yes. All right. Some elements have 2 or 3 of these forms, 2 or 3 different neutron counts that it can tolerate. Some elements just have 1, and it really depends on the element. So, the function of a neutron is to stabilize the nucleus. It glues the protons together. The symbol is a lowercase n with a 0 because it's got a 0 charge, and it has the same mass as a proton. The circle for the line through is the way I write 0 sometimes to make sure that you know I mean 0 and not an O.
That's Jupiter. It's Saturn. It's actually pronounced Jupiter.
All right, electrons have what charge?
Negative.
Negative. Give me the value. -1. All right. What is the function of an electron? Logan, I need you facing this way.
Negative.
Determines the charge of the particle.
Does determine the charge of the particle, but what's its function? Bonding. Bonding. Electrons are the only thing that get involved with chemistry. Protons and neutrons don't get involved in a chemical reaction at all. If protons and neutrons are involved, what's that called? A nuclear reaction. Good. And we don't deal with that in this class. So Beyond this unit, we will not deal with nuclear chemistry. So everything from now on is going to be just electrons. Just electrons. Just electrons control chemistry. Control bonding. What do you think its symbol is going to be?
Is it a P with a negative E?
A lowercase e with a -1 or a negative symbol. It's got a -1 charge. Its relative mass is 0. We need to talk about that. And its function is to control the overall charge in all chemical reactions. Controls the overall charge in all chemical reactions. All right. We need to talk about this 0 AMU because electrons are mass. Are matter. So they have mass. They're actual structures. They are things. How can it have 0 AMU?
Because it's so small even when compared to AMUs that it's like basically
Okay, there you go. So it is, what did they say on that video? How many thousands of times smaller than a proton? It was 2,000 times smaller. And so by that, that's like saying, I'm going to get on a scale and weigh myself, and then I'm going to put a hair clip in my hair and then weigh myself again. My mass isn't going to change did it change? Yeah. But did it change in such a way that you're actually going to need to record that? No, because it's so small. So putting electrons on an atom changes its mass so negligibly that we say it's 0. Okay? So the mass of an atom is all contained in the nucleus. Yeah, protons and neutrons. Good. Okay, isotopes. What are isotopes? You should have a fairly good idea-ish after yesterday.
It's whenever there's...
Wait. Mm-mm. I know why you have that impression, but that's not right.
Is it whenever there's too many protons? So it's a
Mm-mm.
positive.
Same element, different neutron count. That's it. So you can be an unstable isotope or a stable isotope, but isotope itself just means that you have the same proton count, you're the same element, you just have different neutron counts. So let's talk about carbon. How many protons does carbon have? What's the definition of carbon? Good. So 6 positive protons, and let's say it has 6 neutral neutrons. I have a total mass of this carbon of 12 AMU. Yes?
C.
Okay. Carbon, 6 positive protons. What if it has 7 neutral neutrons?
13 AMU.
It has 13 AMU. Carbon 14 has 6 positive protons and 8 neutral neutrons for a total of 14 AMU. Those are isotopes of each other. It doesn't matter if it's stable or unstable. If it's got a mass number, it's an isotope of something. All right. Just as an aside, have you heard of carbon-14 dating? Okay. So in biology, you may have been exposed to carbon-14 dating. What do they use carbon-14 dating for?
To figure out how age.
To figure out how old something is that they dug up. Okay. It can only work. Did you know it can only work for organic remains? There you go, because of carbon. Okay, so just basic biology. Remember, we take in fuel, we convert it to energy, and we use the carbon to actually build our cells. So, and trees do the same thing, elephants do the same thing. Any living organism does the same thing. Takes in fuel, converts it to carbon and energy. Those carbon and energy, that's the building blocks of our body. Great. Did you know that when you're alive, you only use carbon-14? You only use carbon-14. So if you're alive, all the carbon in your body, and I'm talking about me, I'm talking about elephants, I'm talking about bacteria, I'm talking about algae, carbon-14. Okay, well, guess what? It takes a very defined amount of time to go from here to here, because that's a little unstable. It's a little unstable, and so it's going to lose a neutron and become carbon-13. That's a known amount of time. It happens like clockwork. I think it's, I want to say it's just a couple of hundred years. Going from here to here, I want to say it's about 1,000-ish years. I need to look those numbers up because I had forgotten them. But so the point is, going from carbon 14 to carbon 12 is a defined period of years. And so once you die, you stop making things with carbon 14. And so your body starts to decay. And along with that, the carbon decays. So if you are picking up something that used to be alive, you can measure how much of this is in there, how much of this is in there, and how much of this is in there, and figure out what time it died. And it's within just a couple of years. That's how accurate the timeline is.
So is anything old enough to get to 1 or 0?
Yeah, so there are remains that are so old they don't have any carbon 14 left. And in that time, we have to use other dating techniques. And there's also things that are too young. Like this isn't going to help me for somebody that died 10 years ago. This is going to help me date an urn that used to have wine in it, because wine's an organic compound. And so we could take a scraping of that wine and see how much carbon 14, 13, and 12 is in it, and know when that urn had wine in it. It helps with dinosaur bones. You pull up a dinosaur bone, I'm like, I wonder how old this is. Carbon 14 dating will tell you when it died. You don't need to know that, but it's the most practical use of isotopes we have found. I mean, it is just crazy, except for the whole nuclear reaction thing. Questions on that? It's kind of fun. All right. So isotopes. Hey, same atoms of the same element with different mass numbers. Well, that doesn't help you if you don't know what a mass number is. What's a mass number?
AMU. The number of mass.
What is that mass number? Total mass, which is found from protons and neutrons. Good. So protons plus neutrons. That's average mass. It's different. We're going to learn that. All right. There are 2 ways to write isotopes. There's actually more than 2, but I'm going to focus on these 2. You can have the isotope symbol or the isotope name. Isotopic notation is the technical term for the isotope symbol. So if I ask you for isotopic notation, I'm asking for something very specific. So let's talk about that. Okay, you learned this on the Build an Atom Interactive yesterday. If I have the symbol carbon here and I have a 14 there, what's that number?
14. The amount of protons there is.
It's the protons plus neutrons, which is otherwise known as mass number. Good. If it has a number here, what is this? The atomic number. Stop talking over me. Which is what? How many protons it has. If it has a number here, what is it? Charge. Okay. This is called isotopic notation. The mass number is at the top left. The atomic number is at the bottom left. Charge is at the top right. And I need to talk to you about what happens when it's blank. Yeah, take a pass. Okay. That's not where that goes. Would you mind picking that up, please, and putting it in my trash can? Quickly. Thank you. All right. Isotopic notation. I need to talk to you about what happens when these numbers are blank. This number, if we're talking about isotopes, can't be blank. Can't be blank. Has to have something there. But what happens if that's blank? You do, because of that. So sometimes people just get lazy and leave this blank. That is fine, because you're telling me which element it is with the symbol. So these 2 things are kind of redundant. I try to always put it up there, but I don't always have the ability on like the computer won't always let me do this isotopic notation. So if I leave it blank, it doesn't mean anything. So that just means, blank just here just means you're lazy. Here though, what does blank mean?
That it's balanced.
It is neutral. So you are literally telling me it's charged if it's blank. So if it's charged at all, you have to put the charge. You may not leave it blank. If by blank, you're telling me it's neutral. Okay? All right. The second way I can write isotopes is with an element and a dash and then the mass number. So I could write the same thing like this. Carbon and then a dash and then 14. That is not a negative. It's a dash. Exactly. You can also shorthand this by just writing the symbol and a dash and 14. Now, right here though, these two, is there any place to write charge?
No.
So you can't use these notations if it's charged. And you'll notice on your practice from building atom on the back that some of them are blanked out, I think.
So the charge is 0, you can try.
If the charge is 0, you can write it like this. But if it has any charge at all, if it's an ion at all, you must write the charge as a symbol. All right? So just to be clear, I want you to know that you use the word isotopes to describe the relationship between two of the same elements that have different mass numbers. So carbon 13, carbon 14, carbon 12, they're all isotopes of each other. Another way of saying the same thing is that is the isotope carbon 12. That is the isotope carbon 14.
Do all elements have isotopes?
No, not stable ones. All elements do not have stable isotopes. All right. Just FYI, there's pencils back there on that bookshelf. Okay. Ions. Charged particle. A charged particle occurs when protons do not equal electrons. That's what that symbol means. It's an equal sign with a slash through it. Doesn't equal. Protons don't equal electrons.
How is that since you can change the positive? Okay.
All right. So carbon can have two charges. It can be a positive 4 or a negative 4. If it's a positive, I can put the prefix cat in front of the word ion, cat ion, and that means positive. So if I say the carbon cation, I'm telling you which ion I want. I'm telling you I want the positive one. If I say carbon anion, I'm telling you I want the negative. So cat means positive, an means negative, and it's not cation and anion. It's cation, anion. You do need to know that. Make sure you do. How can you remember that cation is the positive and anion is the negative?
Cat is good. Cat has more letters.
Cat is good.
Cats are good.
Good
You
kid.
don't know many cats. It has a T in it.
And T.
It has a T in it, which makes it, which looks like a positive sign.
Oh, and then the and's a negative.
So the cation is the positive one, and the anion is the negative.
That's so smart.
And T.
High five. All right. Valence electrons. Gentlemen, what are the valence electrons?
The one on the outside.
One's on the outermost energy level. What's important about valence electrons?
Bond.
They are the only ones that bond. Inner electrons don't. valence electrons are the only ones that bond. They're the only ones that get involved in chemistry. Inner electrons don't get involved in chemistry at all. They just kind of sit there and hang out. No. Nuclear chemistry refers literally to the nucleus. I only thought of that like 10 years ago, so you're ahead of the game.
Good job, Carlos.
All right. So, sodium. I want to draw sodium. How many protons does sodium need? Good. So, from now on, rather than drawing 11 plus signs, I'm just going to put plus 11, and you know that that's the sodium nucleus. At this moment, I don't care how many neutrons it has. I just care about its protons. All right. So I'm going to draw its first energy level. How many electrons can fit on its first energy level? 2. Good. All right. Is it neutral? This is sodium. No, it's not. It's only got 2 negatives and 11 positives. Jake's have C. So I need another energy level. It can fit 8. Very good. So 1, 2, 3, 4, 5, 6, 7, 8. Is it full? Is it neutral?
No.
Okay. So I need another energy level. And 11. There it is. How many valence electrons does sodium have? Just 1.
Uno.
Gentlemen, get it together. What?
How do we figure out how many
I'm going to show you. Well, how many total electrons? Okay, well, I wanted it to be neutral, right? Because there's no charge there. Well, if it has 11 positive protons, it's got to have 11 negative.
How do we know that
11 positive because it's number 11 on the periodic table. Because it's number 11 on the periodic table.
Because it says it right there in A11.
I mean,
It's like 11 on the
Like,
periodic
the person that made the
Okay, so 11 is 2
okay,
months.
we are going to talk about that in unit 4. That's a very good question.
What unit are we on right now? 2.
Why?
I think we are.
All right. Octet rule. This is a fundamental understanding of chemistry. This explains chemistry. Elements will react to fill their outer energy level. All elements except hydrogen through boron are full with 8. Hydrogen through boron, which means hydrogen, helium, lithium, and beryllium, are full when they have 2.
That why sodium is so reactive.
Elements will react to fill their outer energy level. All elements except hydrogen through boron are full with 8. Hydrogen, helium, lithium, beryllium are full with 2. The octet rule explains all of chemistry, so I want to spend a little bit of time on it. Let's see if I can use this BenQ board without cursing at it.
Whoa.
Out of size.
That's chemistry right there. This is literally DJ.
There it is. All right. Hey,
Go back.
I will. So let's talk about sodium again. Sodium has 11 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. Neutral sodium. Now let's talk about fluorine. Fluorine has how many protons?
I got 9.
9. So it has positive 9 in the nucleus. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's fluorine. It's neutral. Is sodium full?
No.
Because it wants 8 to be full. Is fluorine full?
No.
Because it wants 8 to be full. All right, great. So, can you see what's going to happen so that they can both be full?
They can combine.
Yeah, tell me how.
Well, they share an electron.
No, not share an electron.
They bond. One goes to
Sodium
another.
will give this one away completely. It'll go there. So now it's gone. Ah, now it's gone. How do I erase?
The eraser. No, put your hand flat on the board.
Put my hand flat on.
Yeah.
It's
Just
just
your
your
hand.
hand.
No!
Like spank it.
Yeah.
No! It erased the whole thing. I didn't want that. You all are terrible. I gotta draw it back.
She took back what she wanted to erase.
Oh, I have to circle it? Alright, well that makes total sense. No, I got it. I mean, I don't, but I got it.
Okay.
Okay, so I do this.
Well, they both connected.
Oh! High five. Thank you. Okay, I need your attention. Shh, I need your attention, because this is key. Sodium. Is it neutral anymore? Well, let's figure it out. It's got 11 positive protons. It used to have 11 negative electrons, but now it doesn't.
Oh,
It has only 10, so what's its charge?
positive one.
Positive 1. Fluorine used to have 9 positives, 9 negatives. Now it has 9 positives, 10 negatives. Negative 1. So, everybody, every element, the whole point of chemistry is for every element to come together so they feel full and neutral at the same time. So now everybody's full, but they're not neutral. So what do they need to do to feel neutral? They bond to form sodium fluoride. Now, sodium fluoride is neutral. The sodium has a positive 1, the fluorine has a negative 1. This whole thing is now neutral. And so the elements have done two things all simultaneously. They have become full and they feel neutral at the exact same time, and that is chemistry. That's the whole point of chemistry. And this tells you they need to come together in a 1-to-1 ratio in order to make that happen. Stop talking over me. So 1 sodium and 1 fluorine are neutral together. If they separate, they're not going to feel full and neutral anymore. So they have to stay bonded. That is the whole point of chemistry. All right, well, let's try this a different way. I want to, oh God, let's see if I can do this. Okay, that's cool. Oh, yeah, that's cool. And then I want this one gone. I want this one gone. I want this one gone. Make that one gone. Okay, I did it.
You gotta spank it.
Do you mind not being that awkward around me? I appreciate it. All right, here we go.
How are you?
I want to change this not to that. That was dumb. Don't do that. I want to change this to oxygen. So tell me what I need to change to oxygens to make this neutral. Get rid of one of the electrons. Let's see if I can do that. Okay. Now, go back. Sodium has this electron here. Can sodium make oxygen happy?
No.
Okay. Let's go ahead and switch one over, though. Now sodium's full, but oxygen isn't. So what needs to happen? Whoops. Check this out. Hey. So another sodium. Another electron. How many sodiums do you need to make oxygen happy?
2.
So its chemical symbol is Na2O. I need 2 sodiums, each to donate 1 electron. And so my chemical formula is 2 sodiums and 1 oxygen. So it has a 2-to-1 ratio when it's neutral. Got it? Okay. Do I do this in in a chemical formula?
No.
I do not. I never, ever, 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 ever write the charges in a neutral chemical formula. All chemical formulas are neutral by definition. That is a neutral compound. And so you don't put charges anywhere that's neutral for a neutral anything. So you can put the charge on an element if it's charged, but on that compound, you don't pull those charges down. You're telling me that I need 2 sodiums to make the 1 oxygen happy. Questions on that? Ask them if you got them, because this is an important part. Yes. Yeah. Oh, you always write the positive one first. Always. Yeah.
On the last one with the
Sodium?
sodium,
Yeah.
why didn't they just turn it neon?
Oh, okay. I've got a very good question here. When this is full, it has 10 electrons, right? Is it neon?
No.
No, it's still oxygen. But it feels neutral and full like neon does. It feels like a noble gas. That's the whole point. These guys want to feel like noble gases. They want to feel full and neutral at the same time. So they can't do it by themselves, so they react until they do.
So that is basically neon.
It has the same number of electrons that neon has, but the protons of oxygen. So this does not become neon, because remember the definition of neon is something with 10 protons. This doesn't have 10 protons. It has 8. So it's still oxygen. Really good question.
So they'll react until.
They react until they feel like a noble gas, full and neutral.
So all elements will reach, all matter will want to be stable.
All matter, take the word stable out because that refers to the nucleus, and put in the word all matter wants to be full and neutral.
So that's entropy.
Yes, but we're not going to go there. Not now. Unit 10. We'll go. The same guy in the same seat asked the same question last period. Way too, yeah, for this class.
Who was it?
Some super smart guy, just like Carlos. All right, here we go. Oxidation numbers. This requires some explanation. An oxidation number is the charge an element will have when it's full. Oxidation number is a charge an element will have when it's full. All right. Here is the difference between oxidation number and charge. You ready?
Yeah.
What is the charge of sodium? Right here.
Zero.
Neutral. There is nothing written there. That means the charge is 0. That's its charge. What is its oxidation number? Well, we just saw this up here. Sodium wants to give away 1 electron. When it gives away 1 electron, it's going to have a +1 charge, yes? Okay, so what is its oxidation number? +1. Do you see it? 11 positives, only 10 negatives because it got rid of 1. So it's a +1. All right, questions on that? I need you back. I need you back. All right, let's change this, assuming that I can figure out how to change it. Yes. Here we go. Just give up on it. Instead of sodium, let's make this magnesium, which is 12. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. That's 10 total, 11, 12. That's neutral magnesium. What does it need to do to be full? Give away 2. What's its other alternative?
Or
Gain 6. And it's not going to do that. It's just as easy to lose 1 as gain 1. And so it's going to choose the easiest path. So it's always going to lose 2 rather than gain 6. So when it loses 2, what will its charge be? It'll go from neutral to what? Positive 2. Do you see why it's positive 2? Because if it loses these 2 electrons, it's only going to have 10 negatives and 12 positives. Positive 2. So magnesium's charge right now sitting there is 0. Where's my magnesium's charge as it's sitting there before I marked off those is 0. What's its oxidation number? Plus 2. So I can ask you that information. Even though it's neutral, I can still ask you what charge it will have. Yes?
What if it's equal to go?
Let's do that. Let's do that. All right, get your periodic table. If you don't keep your periodic table in your notebook, you need to, because we're going to be using it pretty much every day.
I didn't get one.
What's your name on it? Yeah. You don't have keep it in your notebook.
Oh, is there a specific case on your table?
I'd like to keep it in the pocket so that I always have it.
Alright, so I'll figure it out.
Yeah, don't pull it down because you'll need to take it out. Yeah. All right. Here we go. Valence electrons. I need your attention. Valence electrons. How many did we say sodium have? 11. No. How many valence? Yes. Put your name on it and keep it in your notebook. 1. All right. And then I just drew magnesium. How many valence electrons does magnesium have? 2. Do you want to draw them out each time? All right then. Memorize this then. You lost it? Lost it? Lost it.
Oh, it's easy. It's just like all the way on. It's so slow.
Put your name on it.
We celebrate birthdays.
Mostly because I have, just, y'all are always on the edge of getting out of control anyway, so add that.
But this class is good though, right?
No.
Oh,
Are you first class?
No.
Who's the worst kid in this class?
All right. So here's the pattern, and I need you to hear this. Y'all, I need you back. Everything in this first column has 1 valence electron. That's why they're in the same column. Everything in the second column has 2. You do not know the valence electrons, and you won't know the valence electrons of any of these inner metals until Unit 4. So let's skip over to here. Boron has 3 valence electrons, and so does aluminum, but you don't know anything underneath that. Let me say that again. Boron and aluminum both have 3 valence electrons, but you don't know anything about gallium or indium or thallium. Carbon has 4 valence electrons. So does silicon, but you do not know germaniums, tins, or leads. And you won't know until Unit 4. Nitrogen, phosphorus, and arsenic all have 3. But nothing under that, you don't know any of those. You don't know antinomies and you don't know bismuth. Same thing with fluorine. All the way down to the metalloid line, you know have 7. Nothing under that. You don't want to tape it, love. Because you're going to be using it every day, pulling it in and out. All right. Noble gases have 8, except helium, which only has 2. Why does helium only have 2 valence?
Because it's
It only has 2 electrons total.
We should write this, right?
All right. Now let's talk about oxidation numbers. Oxidation numbers, remember, are the charge they want to have when they're full and neutral. Or excuse me, the charge they want to have when they're full. So oxidation number is going to be in purple. All right. We already know that sodium has a +1 oxidation number because it wants to get rid of its 1 valence electron. Well, so does everything else in that column. So everything in that column has a +1 oxidation number. We just saw that magnesium wants to lose its 2 valence electrons to form a +2. So does everything else in that column. Everything in that column has a +2 oxidation number. Boron and aluminum both have 3. Is it easier to lose 3 to get 8 or gain 5 to get 8?
Lose 3.
Lose 3. So it's going to lose 3 and become a +3. Carbon and silicon has 4. Is it easier to lose 4 or gain 4?
They're equal.
It's the same. So carbon and silicon can form both a positive and a negative 4. And so how will you know which one is going to form? I have to give you a clue, like cation or anion. All right. Nitrogen has 5. Is it easier to gain 3 or lose 5?
Gain 3.
Gain 3 negative charges gives it a -3 charge. Oxygen. Good. It wants to gain 2 more. When it gains 2, it ends up being negative. You okay with that? Gaining 2 electrons, gaining 2 negative charges makes it negative. All right. Fluorine just wants 1 more, and the noble gases don't want any. Their charge is 0. Their oxidation number is 0, always. Get this memorized. This periodic table will not be up for your upcoming tests and quizzes this unit. You will get this one. Do not use your pink one. You will get this one. It's clean. It has the names and numbers, or excuse me, the names and symbols on it, but it doesn't have anything that we just wrote. So make sure you have that pattern memorized. They're not difficult. Yes, yes? Easy, easy. All right, so let's go back and finish up these notes. So the last thing I want to do is give you this mnemonic to help you remember whenever you're writing charges. Gaining electrons makes it negative, losing electrons makes it positive. You will get it backwards at some point, so try to just keep it into your head. Gaining electrons makes it negative, losing electrons makes it positive. Gillette. So if I say Gillette to you, I mean Gillette. Gaining electrons makes it negative, losing electrons makes it positive. Gillette. No? Maybe? Like up this way? I just drew oxygen in.